And this brings us to the derivative of a function. So the limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus called differentiation. Now, differentiation is the process of finding the derivative of a function. Well, what is the derivative? Well, the derivative of a function measures the sensitivity to change of the function value, which is the y value or the output value, with respect to a change in its argument or the input value or the x value. So we're trying to figure out if you just change the x value a tiny little bit, how much does that impact the y value? For example, velocity is the measure of change in an object's position with respect to time. So how fast you're moving, if you have a little change in time, how far did you go? So the derivative of position with respect to time is velocity. Now, another way to think about derivative, the derivative of a function at a point is the slope of the tangent line to the graph at that point. And that's exactly what we were just talking about. For this reason, the derivative is often described as the instantaneous rate of change. And the process we're going to talk about is how you do that. So this now is our limit definition of the derivative of a function. Okay? So the derivative of a function f at x is given by this right here. What you'll notice is it's the same limit as the slope of the tangent line. So our derivative is really defined by the slope of the tangent line. Now the notation we have here is f prime at x. Okay, f prime at x. And that is going to be a function that is the derivative of f at x. Okay? So a really huge concept here is that derivative equals slope. Okay? It's measuring the change in something, the rate of change. And the derivative can be a function. And we're going to learn how to find these functions. So a couple other notations for derivatives. Okay, so derivatives were developed by a couple different people, Leibniz and Newton, at the same time, and so they actually came up with slightly different variations of the notation for this. But these are the main ones that you're going to see here. So you're going to see f prime at x, and I really like this one because it leaves the function here, and then it gives you the argument. You're also going to see it as dy over dx, and you can think of this as being this tiny change in y with respect to a tiny change in x, dy over dx. You might also see it as y prime. This is a little bit confusing because y to the first or y prime could look a little bit different there. And you're also going to see it as d over dx of some function at x. Now, this notation really is telling you to take the derivative of my function. So all of these are going to be representatives of that derivative. So we want to actually find the derivative of f at x equals 4x squared plus 6x plus 5. And this is going to give us the slope of the tangent line at any x value on this curve. So anytime I want to find the derivative of a function using the limit definition of the derivative, I go ahead and start off by just writing that limit definition of the derivative. So I'm just going to write f prime at x is equal to the limit as delta x approaches 0 of f at x plus delta x minus f at x all divided by delta x. So you are going to need to memorize that, and this is your starting point. And from here, it just becomes a list of substitutions, getting us down to actually find that limit. So the first thing we're going to do is actually substitute x plus delta x into the function. So we're going to rewrite the limit as delta x approaches 0, and this is going to be 4 times. Well, x is now x plus delta x squared plus 6 times x, which is now x plus delta x, and then plus 5. Okay, so hopefully you can see that this x plus delta x gets substituted in for x into our function right here. Now we're going to subtract f at x. So we don't really need to plug x back into the function. We can just literally rewrite the function 4x squared plus 6x plus 5. Now because we're subtracting, I like to keep that in parentheses here. So this becomes 4x squared plus 6x plus 5. Now all of this is going to be divided by that change in x, or delta x. So at this point, we're going to want to simplify everything that's up there in that numerator. So we still need to rewrite the limit as delta x approaches 0. And it's going to be 4 times, well, x plus delta x squared, we're squaring a binomial. And so it's going to be x squared plus 2x delta x plus delta x squared. And then I'm going to distribute the 6, so I get plus 6x plus 6 delta x, and then plus 5. So all of this now becomes this. Next, I'm going to distribute the negative, so I'll get negative 4x squared minus 6x minus 5. And all of this is still divided by delta x. Now we're going to go through the process of simplifying everything in the numerator. We're going to keep doing that. So we have equals the limit as delta x approaches 0. First off, I'm going to distribute 4, okay, to each of those terms right there. So I'm going to get 4x squared plus 8x delta x plus 4 delta x squared. Now everything else I'm just going to rewrite here. So I'm going to have plus 6x plus 6 delta x plus 5 minus 4x squared minus 6x minus 5, and still over delta x. All right, so really important to note that this process looks big, long, messy, but really the only thing I did here was distribute the 4 to get this. Everything else was just rewriting. Now we're going to go through the process of combining some like terms. And what you're going to notice when you combine like terms is any term that does not have a delta x factor is going to zero out. Okay, and so I see a 4x squared right here, and it's going to pair up with a negative 4x squared. Okay, this next one, 8x delta x, has a delta x factor, so that one's going to stick around. The 4 delta x squared also has a delta x factor, so that's not going anywhere. If I look at this plus 6x, there is no delta x factor, and sure enough, I have a minus 6x there. 6 delta x has a delta x factor, so it's staying. And then this plus 5 has its counterpart minus 5. So let's go ahead and cancel all of those things out. We still have the limit as delta x approaches 0. And like I said before, the 4x squared and the negative 4x squared zero out. The 8x delta x has a delta x factor, so it's sticking around. The 4 delta x squared is sticking. Remember the 6x and the minus 6x are going to cancel, so that's gone. The plus 6 delta x sticks around. And then the plus 5 and the minus 5 are gone. The zero's out. Now all of this is going to still be divided by delta x. And this is what we've been doing for a while when taking these limits, is that delta x factor can now be canceled out. And so I'm going to show the factoring limit as delta x approaches 0. We're going to take out the delta x factor from all of the terms in the numerator. So this one will remain 4 delta x, and this one will be 6. And this is still divided by delta x. Now, when you look at this, that delta x will cancel out, and we have 1 over 1. So now, when we rewrite this, we're going to have the limit as delta x approaches 0 of 8x plus 4 delta x plus 6. Now at this point, we can use direct substitution. We're going to plug 0 in for delta x, And when that happens, that term is going to drop out. And so you're going to be left with 8x plus 6. So let's go back to the beginning. What did we start with? We were looking for f prime at x. We were looking for the derivative of f at x. And so if you just follow all these equal signs, we end up here. And so this is f prime at x. It is the function 8x plus 6. Now what that does is it tells us the slope of the function at any x value. So what we're going to do now is actually find f prime at 2. So this is going to be the slope of the function at negative 2. And so since we've already done the whole process and we have the derivative, okay, that slope is going to be f prime at negative 2. And we're just going to substitute that into our function for the derivative, okay, which is f prime at x equals 8x plus 6. So it's going to be 8 times negative 2 plus 6. And so the slope here ends up being negative 10. Now we want to find the slope of the tangent line at x equals negative 2. And so I'm going to give you another equation that's going to put everything in terms of our f of x and our f prime of x. And so the tangent line equation I want you to learn is this one. Y equals f prime at c, so the slope at c, times x minus c, and then plus f at c. All right? So, in other words, we're going to find the equation of the tangent line at x equals negative 2. So we're going to do f prime at negative 2, and then do x minus negative 2, plus f at negative 2. All right, we'll keep substituting. F prime at negative 2, we already found, was negative 10, sorry. And then if we have a double negative, that'll become plus 2. Now, f at negative 2, in this case, they don't tell us the point of tangent c, and so we're going to have to find f at negative 2. And so you can just do a little scratch work on the side. And you have to remember, well, what was f? Well, f is back up here. It's the original function. So it's 4x squared plus 6x plus 5. And so we actually get 4 times negative 2 squared plus 6 times negative 2 plus 5. All right, so we'll go ahead and solve here. Looks like we get 4 times 4 is 16, minus 12 plus 5, and this turns out to be 9. Okay, so f at negative 2 is 9, so we're looking for the point of tangency at negative 2 comma 9. All right, so this is going to be plus 9. Now at this point, we're going to distribute the negative 10 and then combine like terms so that we have it in slope-intercept form. So y equals negative 10x minus 20, and then plus 9. And simplifying, we get y equals negative 10x minus 11. So that should be the equation of the tangent line. All right, what we're going to do now is actually graph this just to see that it works. All right, so I'm going to put in my original function. We'll just call it f at x, and that equals 4x squared plus 6x plus 5. Okay, and there is my graph. We can kind of move that around. And we're going to try to find the slope, the tangent line equation, and we just decided that was at negative 2 comma 9. Okay, so we want to find that tangent line. So when we type in this function for the tangent line equation, we're going to know right away if we're right or not. So I'm going to type in y equals negative 10x minus 11. Would you look at that? Okay, so it's going right through the point, and that definitely looks tangent to me. All right, so that is how to find the derivative using the limit definition, how to use that derivative to find the slope at a specific x value, And then how to use that slope then to find the equation of the tangent line at that x value. Next, we want to talk about a little thing called differentiability implies continuity. And so it turns out if f at x is differentiable at x equals c, then f at x has to be continuous at c. So if you can prove that the derivative exists at a specific x value, then you automatically know the function has to be continuous at that x value. Now, it turns out that continuity, however, does not imply differentiability. So just because a function is continuous at a specific x value does not necessarily mean that the function has a derivative there. So it is possible for a function to be continuous at x equals c and not be differentiable at x equals c. So we're going to take a look at a few graphs here that kind of explores that a little bit. And we want to tell where f prime at x is positive, negative, 0, or does not exist. So there are a couple places where when you try to find the derivative using that limit definition, it's not actually possible because the limit does not exist. So let's talk about a couple situations where a function will not be differentiable at a point. The first one is going to be where the graph is not continuous. Okay, so if you have a discontinuity in the graph, then you will not have a derivative there. Another place is where the graph has a sharp turn. Okay, so it just abruptly changes direction. You're not going to have a derivative there either. And the last thing is where the graph has a vertical tangent line. So there are a couple functions that will come and then all of a sudden they'll shoot straight up just for an instant moment and then come back down. And right at that point where it's vertical, you're not going to have a derivative. So let's talk about then what's going on here. So what we're going to do is label the derivative as being positive, negative, 0, or does not exist at each of the points on this curve. Okay, so let's just look at the first one. So right here, down at the bottom, this definitely is increasing, and so our slope is going to be positive here. And our slope is positive here, and our slope is positive here. So if the slope is positive, that means the derivative is positive. Now, when you do this, you can see that it's not quite as positive as it had been before. The slope is kind of slowing down. And when you get to the very top here, you're actually at a slope of 0. Okay, the function is neither going up nor down, and so the derivative is 0 there. Now when the function decreases on the other side, this is negative, and then a little more negative, and all of those derivatives would be negative at those x values. So let's try for the next one. Looks like positive, 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 slowing down, 0, negative, 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 0, and then back to positive. So this is just a little chart to show the sign of the derivative. Now if we look at our next one, this one starts off positive, and you notice that it's a straight line. And so it's really going to be a constant slope or a constant derivative all the way up. Now right here, we have a sharp turn in the graph. It abruptly changes directions. And so the limit doesn't exist there when you try to use the limit definition. And so we're going to say does not exist. And the reason is there is a sharp turn in the graph. So sharp turn in the graph. Now coming out the other side, looks like it's negative, and that's also going to have that constant slope. All right, looking at the bottom left. So this is kind of weird, but this function is slowly negative here. And then it really starts getting negative as you get closer to this vertical asymptote. Okay, so that vertical asymptote right there. Now, what's strange about this one is when you come on the other side of the vertical asymptote, your slope is still negative, very negative as you're closer to the asymptote. And then still negative, still negative, still negative, still negative. So this is a function that is always decreasing on its domain, and the derivative is negative everywhere that the function's actually defined. Now, what's happening here at the vertical asymptote? Okay, well, at that x value, the derivative does not exist. And that is because the function is not continuous there. Okay, so any discontinuity, the derivative will not exist. Our next example looks like we have this flat horizontal line, and the slope of that horizontal line is 0. So that means the derivative is 0 all the way along there. Now, at this x value right here, we actually have a jump, and it's a jump discontinuity, and so we know that the derivative does not exist right there, and the reason is it's not continuous. So we learned about all those discontinuities, and that's one of them. And then when we come out the other side, it looks like the derivative is 0 again because we have a horizontal line and the slope is 0. Now in our last example, this is going to be, looks like just a linear equation, okay? And that's just going to be plus, 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 plus. And in this case, f prime at x is going to be constant. And what's interesting about that is when you were doing Algebra 1, you remember this equation, y equals mx plus b, and you learned that m was the slope. And the slope is always constant, okay? And so that slope is actually the derivative of that function. Kind of interesting stuff. We're going to talk about that more later. But this is how to tell where a derivative is positive, negative, or 0 based on what the function's graph looks like. And you can also tell where the derivative might not exist. All right, so that is it for our lesson 2.1, the tangent line, and using the limit definition of the derivative to find a derivative as well as the equation of a tangent line.